In the previous video we were looking at type 0m tensors. In this video we are instead going to look at type nm tensors for generalization. These are defined as linear maps from type 0n tensors to type 0m tensors. Letting T be a type nm tensor and S a type 0n tensor, noting here that what is written should be 0n, T of S is a type 0m tensor. Following the previous lecture, this means that we can write out the components of T of S with subindices a1 through am, and that these were defined as T of S acting on the basis vectors ea1 through eam. We can introduce a basis for 0n tensors in the following way. We define a set of tensors ea1 through an with the indices upstairs through their action on a set of basis vectors eb1 through ebn. And this is defined to be the product of a series of deltas, delta a1 b1 through delta an bn. In particular, for the tensor S, we can write its component S a1 through an, which we defined as S acting on the set of basis vectors, as S b1 through bn multiplied by these delta functions, delta b1 a1 through delta bn an. But with the definition of the basis, this is equal to S b1 through bn multiplied by the basis tensors, acting on the same set of basis vectors. This means that the tensor S must be written as the component S b1 through bn multiplied by the basis E b1 through bn. With this basis at hand, we can take the components of T of S and expand the argument S in terms of this basis. Then, using the linearity of the tensor T, we can pull the components outside, leaving us with the components of S multiplied by the components of the tensor T acting on the basis tensor E b1 through bn. And we now define this object T b1 through bn, a1 through am as the components of the type nm tensor T. As an example, let's look at vectors and see that they can actually also be seen as type 10 tensors. By definition, a type 10 tensor should be a linear map from 0,1 tensors to the real numbers. Given two different type 0,1 tensors, omega 1 and omega 2, they are maps from vectors to the real numbers. Their sum is defined as omega 1 plus omega 2 acting on a vector v being equal to omega 1 acting on v plus omega 2 acting on v. The multiplication of omega 1 by a scalar k is defined as k multiplying omega 1 acting on v. Given a fixed vector v, we can define its action on 0,1 tensors through precisely these relations, which makes v as a map from 0,1 tensors to real numbers a linear map. In component form, v acting on omega, being defined as omega acting on v, is omega acting on the basis vector ea multiplied by the vector component va. This is omega a va, which can also be written as omega a multiplied by the vector v acting on the basis tensor ea. And we should here note that this is equal to omega a multiplied by the inner product of v and the dual basis vector ea. As we now have seen, vectors in Euclidean space can be seen either as a type 0,1 or type 10 tensors. This has been predicated on the existence of an inner product. However, it will no longer be true in a general space where there is not necessarily a metric that defines such an inner product.